This instructional video is designed to show you the properties of a quote-unquote good wave function, namely how orthogonality and normalization, which taken together are orthonormality, can work to simplify something that seems relatively complex. So let's use a mixed state, which is allowed from the first postulate. So we'll define the full big wave function as a linear combination of smaller wave functions that we already assume are orthonormal eigenvectors of the operator in question. So what this means then is that these have the property of being normalized with themselves and orthogonal to each other. In order to make this a bit simpler, we're going to limit it to just two. So we can write out that the whole thing is going to be some C1 times little psi 1 plus a C2 times a little psi 2. So now, if we want to then figure out what the average value of some operator is, we have a rule for that. So we have some operator, and we would need to take the integral over all space, psi star operator psi d tau. Now, this comes from the fourth postulate, but in order to actually simplify this down, we can take advantage of the fact that these are orthonormal eigenfunctions of this operator, in which case we'll have the following additional piece of information that we want to take advantage of. That we get some characteristic eigenvalue as a result of applying the operator. So at this point we have everything we would need to evaluate this integral. So the first thing we want to do is substitute in for the full wave function. So our average value, we're going to have the integral, and because this is the complex conjugate, we want to conjugate everything. Operator, and then the regular version of the wave function. So now at this point we've expanded all this out. Because this is a linear operator, we can distribute it across both of these and get results for them. So we'll rewrite the first half of this integral, C1 star, psi 1 star, C2 star, psi 2 star. And now the result of the operator acting on this is that you'll get A1, C1, psi 1, and A2, C2, psi 2. So now at this point, we've got a bunch of constants and a bunch of functions. We're multiplying things together, and that's all straightforward. We can just apply FOIL. So we'll have integrals of several things, and that integral of the sum is just the sum of those integrals. So I wanted to distribute everything and multiply through. So we want to do the first. So we get an A1, C1 star, C1, psi 1 star, psi 1. Outer, that's A2, C1 star, C2, C1 star, psi 1 star, psi 2. Then we're going to do the last two down here. We're going to have the inner, so that's A1 with C1, C2 star, psi 2 star, psi 1, and then the last, which gives me A2, C2 star, C2, psi 2 star, and psi 2. And all of these with our variable of integration. So now at this point we want to take advantage of orthogonality and recognize that any integral that has two things with different indices will be 0. So the integral that we would get here and the integral that we would get here are going to be 0 because 2 does not equal 1, 1 does not equal 2. So the ones I've circled in red will end up being 0. And finally, we can take advantage of normalization and recognize that while these integrals survive, we know the exact value of it. These constants will pull out, and so this part will be 1, and this part will be 1. So at that point, all that remains to be done is write up the surviving terms. So for the average value of the result from this operator, we only get the terms that have matching orthonormal functions. So we get A1, C1 star, C1 plus A2, C2 star, C2. And so if we understand properties of a good wave function, being orthogonal and normalized, it's possible to very quickly go through all of the terms in any seemingly long and complicated integration and simplify it down to only the parts that survive, and then we figure out what we get from the constants.